I'm very well aware that this says section 3.7. However, in my learned many years of experience, this belongs in chapter 4, and I'm going to teach it like that. I look at any chemistry college or otherwise, I just have never seen another author teach it the way this one does. So I'm going to go like I think it should be. So here we go. The different types of chemical reactions. Here's what I'm going to expect you to do in chapter 4, well, in this format. I'm going to expect you to be able to identify a reaction, a chemical reaction, and tell what kind of reaction it is. Not only am I going to expect you to be able to do that, I'm going to be able to expect you to, if I give you the two reactants, or one reactant even, tell what the products are going to be with accuracy. Predict what the products should be. Now, the single most important thing to remember here when you're doing these reactants and products of chemical reactions is to focus on writing the correct formula. You're going to hear me say that so many times, but it's the number one thing that trips students up, is they don't write their correct formulas. And if you have not learned your polyatomic ions yet, you're going to be in so much trouble. You're already going to be behind if you have not learned those polyatomics that I asked you to know. If you do not understand that when you have those 7 diatomics that I also asked you to know, when they are alone, they must have a subscript of 2 beside them. Several of you did great on the homework where I asked you to name and write formulas. Some of you did not. And then there were a great many, unfortunately, that did not choose to do that homework set or the quizzes on that. There was a reason that I asked you to do those kinds of things. So if you did not, and you need extra work on that, you really do need to review over those things. So let's talk about the types of chemical reactions. There are 5 of them. Generally speaking, there are 5 types of chemical reactions, although some of them can be classified, like a combustion is one of those, that can be seen as a type of a replacement, but we're going to discuss that here shortly. So let's go. Let's get after this. The 5 types of chemical reactions, the first of those is called a combination. Now, I'm going to also call it a synthesis, and I'm going to call it a synthesis simply because the word combination and the word combustion are very close together. And because they're very close together, it's easy to get these 2 words, combination and combustion, confused. And when you see those 2 side by side, they very much look alike. So combination or synthesis. And besides synthesis, let me spell it correctly, please. Synthesis describes what's happening. It's being synthesized or formed or made. That's what's happening. So a reaction in where you have 2 or more reactants that join together to become one single product. That is a synthesis. And this is how you can recognize it. It is the only one of the 5 types of the reactions that has one and only one product. That's how you're going to recognize it. If I list a set of chemical reactions and I ask you to, and I will, that's going to be some of your matching homework, what kind of reaction is this? And I ask you to identify that. That's how you're going to know a synthesis or combination. It's going to be the one that has only one product. All right, we're good there? The second type of chemical reaction that you're going to need to know about is its opposite. If things can be joined together, then they can also be torn apart. And that would be a decomp, or decomposing, splitting apart. So it is the one and only of the 5 types of chemical reactions that begins with a single product. Notice there is no plus sign on the left. I also want you to notice this little triangle. This little triangle up here is the Greek letter delta. And in math or science, it means you add heat or change. So in this case, this Greek letter delta means you had to heat it up in order to make this reaction occur. So this says you're going to take some calcium carbonate, you're going to heat it up, and it's going to produce, split apart, and make calcium oxide and carbon dioxide. Calcium carbonate is lime, and so when you heat it, when it gets hot, it makes calcium oxide and carbon dioxide. Decomp. You recognize it from the 5 types because it's the only one that has one and only one reactant. We've already talked about a little bit combustion. I usually save combustion for the 5th type of reaction, but I will go ahead and discuss it here. Combustion looks like one of the other 5 types called a displacement, a single displacement, except for 2 important exceptions. First of all, one of its products is always going to be O2, always, okay? And the other is that it's going to have a hydrocarbon. When your gasoline burns in your automobile, you put a hydrocarbon, you put octane or butane in your gas grill, or propane, you put some sort of hydrocarbon, or you burn alcohol in a alcohol burning fireplace perhaps. This is a hydrocarbon. A lot of times hydrocarbons will not have this extra oxygen right here, which is fine, and sometimes it will. Okay, if it's a complete combustion, then it's going to be CO2 and H2O. Now, here's the trade-off. Combustion reactions are always the easiest to predict, but they're also the hardest ones to balance. I'm going to give you a few tricks on how to balance them. They're always the easiest to predict because they always have the exact same 2 products. They always have CO2 and H2O. The other product is always heat because it is combustion, it is burning. So you always also have heat. And I usually always add that in. Even though you don't balance it, it is a product. That's the reason that we do combustion reactions in the first place, is to generate that heat. So a lot of times in these kind of reactions, you will not be told about the oxygen. You will have to assume that it's there because combustion reactions cannot occur without it. So you will have to add in this oxygen by yourself. You will have to be told. You will not be told, rather. You will just have to assume and have to add it in. And it is O2, not just O, because it's diatomic. All right. We're going to work on balancing these and work on predicting products here just shortly. You'll see what I'm talking about. And then we have the last 2 kinds. Well, here's these right here. She gives some examples in this. It asks you what kinds of reactions are these. And I hope that by now that you can see, let's look at some tips right here. Letter A has only a single product over here. One product. So I hope that you can see, because it has just one product. I'm not going to call it a look at this combination and combustion side by side like this, or up and down from each other. Easy to confuse, so I would rather us call this one a synthesis, and that's what I'm going to call it. Only one product, synthesis. Okay? Look at letter B. You have 2 things on both sides of the yield. 2 things. If you got 2 things on both sides, it can't be synthesis and it can't be decomp. Therefore, it has to be one of the other 3. And if you'll look at your products, you have CO2 and you have H2O. If it's CO2 and H2O as your products, I'm going to look at my reactants also, and I see in my reactants I have only carbons and hydrogens over there. If I have only carbons and hydrogens, it must be combustion. And then this third one, I have only one reactant. And what I would ask my students to do is I would not only ask them to tell me what kind of reaction, but how do they know? How do you know that letter C is a decomp? I would ask you to be able to tell me because it has only one reactant. That's how you know. All right, let's look at these last two kinds. She goes on into chapter 4, which is exactly what I'm going to do. All right, the last two, Dr. Burge in her text, she just doesn't specifically call them by name, but the last two are called displacement reactions, and they are single displacement and double displacement. And in section 4.2 in the text, she does definitely address double displacement, and this right here is an example of a double displacement reaction. And in both of these types of reactions, something has to push it. Something has to force this one to happen. And so you are going to need to know these types of things. In a double displacement reaction, notice some things that have to be true. In a double displacement reaction, or I've always called it double replacement or double displacement, either one will be fine. This is called a precipitation reaction, and the reason that it's called a precipitation reaction is because in this particular one, notice everything is in aqueous solution. So these are dissolved in water, and notice something else. You have an ionic compound here, you have an ionic compound here, and they're both dissolved in water. Okay? And over here you have, this is still dissolved in water, but look, this is a solid. It settles out. It precipitates. A solid that settles out of two liquids is called a precipitate. So this forces this reaction to happen. So basically what happens in a double displacement reaction is that you have this beaker and this beaker. They're both got water in them. You pour this, in this case lead nitrate, and this sodium iodide in there, and you mix them up, and they dissolve. You can't see them. They look like just clear water, like you put sugar or salt or something like that in there. But when you pour them together, this one stays nice and clear. But this one, when you do it, it forms a precipitate, and that precipitate settles to the bottom. And when it settles to the bottom, it's no longer floating around. And so these little particles, they had split apart from each other, and they were just floating around. Their little ions were floating around. That's called dissociation. And so they would bump into each other every once in a while. But these guys, this lead and this iodide, when they bumped into each other, they stuck together and formed a solid that could not stay dissolved in water, and it sank to the bottom. And so that forced the reaction to happen. The rest of them, they all stayed dissolved in water. And so this forces this reaction to take place. Precipitation reaction. But the overall type of reaction is called a double displacement or a double replacement. Notice its characteristics. You have not one, but two compounds on both sides. Do not confuse this with a combustion. Combustion does not have two compounds on both sides. This one does. All right? And then here's what happens in this kind of reaction. You have two ionic compounds. I'll show you with something very simple. One of the simplest ones that is done in a lab. Let's take some good old table salt, some good old sodium chloride, and some silver nitrate. Some of you may have seen this one in a high school chem lab. Here, if you were to have made these together, you put this in water, in an aqueous solution, and you put this in an aqueous solution. As soon as you do that, these two split apart and form silver ions and chloride ions. I said silver, I meant sodium right there. And this forms silver ions and nitrate ions. Now, what happens is that this positive cation and this positive cation will trade places. They will trade places. So this goes with the nitrate here. And then this one, let me change colors, will okay, now let me show you and see if I can hopefully keep you from making a couple of mistakes that students make. First of all, please make sure that you leave the cations in front. And secondly, please make sure that you write correct formulas. What would be the correct formula when you put this sodium together with this nitrate? This has a +1 charge, this has a -1 charge. Please remember what you learned. Please do not try to move this 3. It is part of nitrate, that polyatomic ion that I asked you to learn. So this would be NaNO3. That is the correct formula for sodium nitrate. Plus, now let's write the formula for this other one. A very common mistake is for students to do this. And this is wrong. You will always must put that cation first. Silver has a +1 charge. Chloride has a -1 charge. So this correct formula is AgCl. The cation must go first. This forms a solid. And if you will notice in your textbook, in Chapter 4, it lists for you solubility rules and tells you what things are soluble and what things are not, so that you can find out which of these two. Is it going to be the sodium nitrate, or is it going to be the silver chloride that is going to allow this to happen? And you're going to see that in this particular one, it is the silver chloride, because on page 132 at the top, page 132, it tells you that in water insoluble compounds are compounds that's, well, let's see, containing carbonate, phosphate, chromate, sulfide. Oh, there's got to be some more on that other page. I'm sorry, page 131. It tells you water soluble compounds. It tells you that chloride is, except if they contain silver. That's the bottom of page 132, table 4.2. It tells you that. So you're going to have to look at that table so that you know which of these two things, and this would be an S in parentheses to show that this right here is the one that is soluble. I mean, that's going to form your precipitate and settle out. And then you would go back through and balance that as well. That is how you do these precipitation reactions. And the last kind of reaction that there is, the fifth kind, so far we've been over 4, the fifth kind is a single replacement. And single replacement reactions, or single displacement, whichever you want to call it, I believe she addresses as well in maybe section 4 or 5, which is, I'm not even going to go there, but there's a table on page 4, on page 145. She talks about single displacement. So let's talk about them as well. The last kind of reaction that there are, and then we're going to do a quick review. Single displacement. In the single displacement, what happens here is that you're going to have a single element and you're going to have a compound. Let's call the compound AB. And let's call the single element C. And what happens is C comes in, and if C is a metal, which it most of the time is, it's going to come in. It's positively charged, so what's it going to come and take? It's going to come and take this positively charged because it's in front. So you're going to end up with CB, and it's kicking A out, so A is going to end up by itself. Now, this reaction will not always happen. This reaction only happens if C is more active than A. And there's something called the activity series. That's on page 145 of your text that says which elements are more active than others. And if the element is higher up, this element, this single element, C in this case, is higher up than the one it's trying to kick off, then it's big enough and bad enough to kick it out and take its spot. But if it's not, if it's lower down on this activity series, then it cannot. Now, you will not have to know this activity series. You will always be given the activity series. I don't know of anyone that would ever expect you to have that memorized. So you will always be told of this. So let's show an example of when this kind of thing would happen. Here's an example of one that would not happen. Here's copper, a metal, and here's some zinc chloride. And if you'll look on the activity series on page 145, copper's all by itself, and it's going to come in and try to kick off the zinc. But zinc is in the middle, and copper is very close to the bottom. So this one is not going to happen because copper is lower down on the activity series than zinc. So you would write in no reaction. Just like that. No reaction is going to take place. Now let's do another one, and then we're going to recap. What if you had, let me go back to the activity series. What if you had some sodium chloride, let's get back to good old sodium chloride, and you had some potassium. Then what would happen? Would this reaction take place, yes or no? Well, potassium is second from the top on the activity series, and it's going to try to come in and kick out the sodium because it's in front. If this is a metal, then it's going to come and try to kick off the cation. And you can see that, yes, it's way higher than the sodium. Sodium is like 4 or 5 down from potassium. So yes, this one's going to happen. So what's it going to form? Well, we have to focus on writing correct formulas, so we're going to split up the sodium and the chloride, so you know sodium is going to end up by itself over here. Do we have to put the little 2 down below? No, because it's not a diatomic. So we're going to focus on writing correct formulas. I'm going to use the chart to tell me what is the charge on potassium. It is +1. What is the charge on chloride? It is -1. So what is the correct formula when I put these two together? KCl. This is the correct formula. And then I would go and balance that. Okay? Well, let's do a quick recap of the 5 types of reactions. The 5 types of reactions are: number 1, synthesis, also known as combination. I will also put this on Blackboard for you. The second kind is, change colors for that one. The second kind is decomp. These are opposites of each other. Synthesis is bringing together and you get one product. Decomposition is only one reactant. That's how you know it. The third kind is single displacement. These don't always happen. This only happens is if your single element is higher up than the one it's trying to replace. If it's a metal, it's going to try to replace the metal. If it is a non-metal, and those can happen too, it's going to try to replace the non-metal. Okay? Then you have double replacement, double displacement. And lastly, you have combustion, burning. Always the exact same 2 products. Always. If it's complete combustion, which we hope it is, it's always going to, on the product side, going to be CO2 and H2O. Okay? And it's always going to be some hydrocarbon and oxygen on the left. Alrighty.